I hope we are glad to be back. Now, I'm going to discuss impedance matching, all right, and impedance matching and its importance, all right, in communication systems. Wow, you could not match your impedances, you're going to have nightmares. In fact, generally, impedance matching, if impedances are not matched, there's a lot of power losses. Let's see how these power losses okay. Let's take a scenario. Let me start with the Thevenized situation here. I'm basically going to get a copy of this and put it here. Let's say now, let's imagine a scenario where we have actual values. Let's have a value there. That value, okay. Those must be ungrouped first. Alright. Or rather, I could have just used a different rubber. Alright, let's suppose with a scenario where we have a supply. Let's take a simple supply of 10 volts. I'm going to use DC to explain this, even though it works equally with AC. Let's suppose our internal resistance for the system, or the system resistance, is definite. So when it's definite, it's more like the internal resistance of the system, okay, but it's the system, or what we call the characteristic impedance of the system, all right? That impedance, let's suppose it's also, that whole thing worked out to 10 amps, onto 10, ohms. I want to highlight something here, all right? Remember now, we can change this value from anything from 1 up to 10, all right? Let's go. Let's start with 1. Let's say we closed our system there with a 1. A 1 ohm load. Okay? Let's calculate the current here. We know that, okay, this is very nice. So this is our system, our overall system impedance. Now let's suppose that we have this. It will mean therefore that the total current there, that the current to the load IL would therefore be what? IL would be it will be VTEV or V supply. In this case, we use V supply, but it will be VTEV in a terminal situation over a total of 10 plus 1, which is 11. All right, let me rather use this. Let me rather say, I don't want to lose people, so let me rather say V in, getting lost here. This is R of the system, the voltage of the system over R of the system, or R Thevenin, right, plus R load. This is our RL. We keep changing the value of RL here, okay, in our experiment. Now, let's suppose the situation we have here, it means that we've got a supply of 10, or with a what? With a resistance of 11. That will give us a current of what? If we take a calculator there, that will be 0.99, but let's prove it. This is 10 divided by 11, 0.99. This will be 0.9. I'll ignore the units for now. I'm just want to illustrate something. This is repeatedly, okay. That is what we have, okay. 0.9 is our what? Is our current. Now, if you want to calculate the power, because this is about impedance matching, is about power transfer, it's about maximum power transfer. Maximum. We want to transfer as much power as possible. We don't want to lose power. Power costs, not only does it cost us money, it costs us a lot of work to get that power. So we don't want to lose our power. So this is about maximum power transfer. Okay, so now if you look at this thing, what is our formula for power gain? Power can be I squared R. We've got I, we've got R. So we are going to use I squared R. Now our I is 0.9 repeatedly, and then this is squared times an R of 1. Alright, so that will give us something like, let's square this, x squared, and then times 1, it won't change. That will be 0.826. So our power here is equal to 826 milliwatts, 0.826 watts. Okay, so now this is our power in the first instance. So our our load was that small. Now there's a great mismatch here. There's a 9 ohm difference here. All right, let's go on and have increase our load to 2. All right, let me have a table here. Should I have it there or there? I'm trying to see where it won't take too much space for me. Just want to deal with not too many. I don't want to have too many. Let's have what call this um, our load here, RL, and our power here. I just say P in watts. All right. That will be, we have an RL. One day when you try and use this, you realize how I'm not really as messy as this. Is a little bit difficult. This is 1, and we had 0.826. Let me rather say 0.8. Okay, let's go on and use double that power. Let's double that load to 2 ohms. All right, when you double that load to 2 ohms, okay, now this was power at what? At 1. This is 1 ohm. Okay, now let's have 2 ohms as our new load. So we change that to 2. Right, what do we have now? Our I changes to, our I changes because, let me move this because it's squeezing up. Let me move this whole stuff a little bit to the Control Z. Let me take all of it. I seem to have missed a corner there, and then move it a little bit to the side there. I'll keep doing my work on that place, so that I can have my table is not disturbed either, so I can have my table in the middle here. All right, so now I'll keep changing the values there. All right, now we have a scenario where our RS remains the same as the system. So this is 10 plus 2 now because we've changed to 2. So this is going to be 10 plus 2, which is 12. Okay, which changes our what? Our current, our IL to 10 divided by 12. Right, that will be 0.833. Now that will be 0.83. Right, little change. We just doubled the thing. What happens here? Our new power now cannot be the P at 2 ohms. The power now, when you've got 2 ohms, this has changed. Okay, this has changed, and then this is now what? When we now say 0.83, 0.83 squared, the resistance is no longer that. Resistance is now 2. So what do we have now? This squared times 2, and we have 1 comma what? Our power has increased somewhere. So wow, we think that as we increase the resistance, you would assume that with a bigger resistance, you must have less power. You would assume that. So a lesser load doesn't necessarily mean greater power. Now you've got a bigger resistance, and our power has gone up to 1,39, 1,389, 1,389 watts. Okay, so it is almost not really doubled, but 1,4. It has gone up to 1,4. I'm just gonna keep it simple here because my you can see what the values are there. Okay, the actual values are, it's actually higher than that. That 8 is repeated. I could have simply said I prefer to do things the mathematical way, the proper way. This should have been 1,38 repeatedly because it goes on forever. All right, now this is nice because it's easy to then convert it back. If you want to convert it back to your fractions, it's actually easy. Okay, so you've seen how we've doubled the load and you've think. So let's see if the pattern goes on. We will now change our power to, we will now change our load to 3 ohms. I won't keep writing ohms here because it will make us slow. Maybe slow is not bad, so that people understand really what we're doing here. Now we will, I think I must prefer the other rubber. Doing this forever is something else also. Alright, now, so we increase our load to 3 ohms. Okay? I will not do 3 all the way up to 3. I will do these successful ones, then I will start skipping. Alright, just to highlight what I'm doing here. Alright, now, let's me rather go straight to 5. Shouldn't I just go straight to 5? Let's do 3 last, then we'll go to 5. Now, let's go and say, alright, you've got now a new scenario where your power is what? Your power at 3 ohms is going to be, this is still 10, the system resistance plus a load of 3, so it's now 13. 10 divided by 13 is going to give us something like 0.769. Less current, 0.769. Well, it's going on. I'm only testing 3 decimal places. And when you square that, and then multiply that by the load of 3, and as you can see, our power keeps increasing. All right, you increase the resistance, the power increases. So this is now going to be 0.769 squared times 3, and it gave us a whopping 1.775. Where it's 3 decimal places is still going on, so I will simply say 1.8. So it's considered that as we increase the power. So let's skip 4, let's go straight to 5. Okay, I'll go to 5. Let's change our power from what? From 3 to 5. And I said I'll change this rubber because it's a little bit, now this is a little bit faster. I can simply cycle the whole stuff. Oh, it's grouped. Alright, let's ungroup. Let's ungroup it. Ungroup. Alright, now let's go in and say what? My rubber, I go and say I want to remove this. It's still grouped. How come? I just ungrouped it. Is it ungrouped? Yes. Alright, and then obviously that changes. We're now going to go to 5. No, I don't want to remove that. I want to remove that. I want to remove this, and I want to remove that. We're now at 5. So we are going to say our power, when the resistance is 5, that is going to be 10 over 15, because it's in is 10 and 5. So it's going to be 15. 10 over 15 is actually what? 0.66. Let's just satisfy people. 0.66. 0.6 is enough. Okay, 0.6. That is our current. We square that, and then we get 0.44. Oh, okay, 0.6. If we square this and we multiply by the new load of 5, and we've got times 5, and it gives us 2.2. So yes, it has gone up. It's actually 2.2 repeatedly, and that is 2.2. You can see our what? As we increase the load, our so far it suggests that as we increase the load, our power is also increasing. Let's go straight up to 9, because now I think we agree that it will keep increasing. Let's go up to 9. All right, and when we have our thing at 9, our load at 9, this is no longer true, that is no longer true, this can't be true anymore, and obviously this will not be true. We have to calculate new values. Now this will be 10 over 19, because 10 and 9, the new 10 and 9 will give us 19. Okay, 10 divided by 19, it's almost half. Okay, by 19 must be 0.526. 0.526. This was higher than what? 4. 9 is higher than the thing, so you can see it's going to be higher already. But anyway, 0.526 to 3 decimal places. 0.526 or 526 squared. That's our power formula times our resistance of 9 is much higher. Now you can see that this is going to be squared and times 9. that will be 2,5, 2,449, 2,493. Okay, then we'll round off to say 2,5. Yes, our power has consistently been going higher as we increase the load. Now let's get it to 9,8, 9,9. Okay, if we have that as 9,9, all I change is 9,9, that becomes 19,9. This is no longer true, the other values are no longer true, so I will remove that, and I will remove this. Alright, and our new calculation now says 10 divided by 9,9 is almost, really this is almost half. 10, the supply, 10 plus 9,9 is 19,9 divided by 19,9. This is 0,503. Okay, that is 3 decimal places. Now 0,503 is our new current. We square that for the power formula, multiply by the resistance 9,9. Okay, so if we do this, we get a power of this squared times 9,9, and you get, well, 2,49993. I want to illustrate, because 2,5 is going to confuse us here. I want to illustrate that it's still higher than what it was previously. Okay, this was way to round off to make it 2,5 last time, but even if you round off, it's the increase. It's like the increase is not linear. The increase is not linear. It is more like that. Oh, no, that is increasing. That is increasing. It shouldn't be increasing. It is more. It's increasing, but it starts off fast. The difference, small difference, make it thing, but it starts to level off. Okay, it's increasing. You see now when you make it exactly 10 there, so we still have what looks like 2.5. If you are using, you are going to be deceived here, because we use only two decimal places. If we reduce more, you're going to see that that difference was going to be what? There was going to be a difference. This was going to be higher still. This was going to be an increase from this. So it's still increasing. 2.5. But this 2.5 is higher. It's actually misleading. When you put 10 exactly, we match the impedance. You see this is 2.4. It's only 2.5 by rounding off. Let's match it and put it exactly at, I think you can see this is going to be 2.5, but anyway, because this is going to be 10 over 20, but anyway, let's prove it. This is 10 and 10. So this is going to be 10 plus 10, which is 20. That is 0.5 exactly, without a need to round off. There's no comma anything. So this here is going to be 0.5 squared, which is 0.25. Now, then there, that is what? Times load of 10, that's exactly 2.5. Okay, so this did not get promoted like the 2.49s that we had previously. This is exactly 2.5, so it's actually even higher than the other 2.5s, because these were rounded off 2.5s. All right, it was a lesser value, it was a higher value, it is exactly 2.5. All right, but these were only promoted by rounding off. All right, now if I use 3 decimal, probably I should have used 3 decimal places to better illustrate this. Probably I should go back just for thing. We lose nothing. This is exactly 2.5. 2.5. This is 2,4939 here. Okay, this was, I do not remember that, but let me quickly do it. It was 9, so it was 10 divided by 19, and this was squared, and then multiplied by 9. It gave us 2,4. You see, this is 2,49. This was 2,493. So you can see this is 2,493, 2,499. This is 2,5 straight. So there's been an increase. All right, there's been an increase. Let's go slightly higher to 10,1. Okay, if you go to 10,1, all that changes is that this becomes 20,1, 10 plus 10,1, that will be 20,1. Now that you will see. Now we expect it to go up because the trade has been going up. Let's see if that's the case. Right. So that is that 10 divided by 20,1, and we have now 0,498. In to two decimal places, 0,498. Three decimal places. Now, when you multiply that, then when you multiply that 0,498, and then you multiply by the 10,1, what do we get? 0,498 x squared times 10,1. We get, it is dropping again. It has gone back 2,49. It has gone back to this value here. It is dropping 2,4999. That's what it's giving me here. All right, so it was peaking at 10. We said it was going up, but now it peaked at 10. Now it starts to come down. Okay, it starts to come down. This is, I'll round off to 2,5, but as you can see, the actual figure is actually less. All right, now we go on and say, okay, let's extend our table. And group. Let's extend our table. Do experiments on the higher side. We're below the, what call this? We are below the system impedance. Now we are rising above it. Let's see what we get. There we go to 11. If we have 11, that there changes to 11. Currents will change. That will change. This will change. Okay, so now what's happening now is that we will have 10 divided by, this is 11 now. We said our new value is 11. So this is going to be 10 and 11. 10 and 11. System impedance doesn't change. The load has changed to 11 is 21. 10 divided by 21. That's our current there is 0,476. 0,476, round it off to 3 decimal places, 0,476. Fit it into our formula there, square that times 11. That will be that squared times 11. And it gives us 2,494. It comes back here, 2,49. This one was 4, this one is 2,494. 2,494. But it may mislead and it may look like 2,5 was with only 2 decimal places. We don't see the very, my table was a little bit bad, but at least you're able to see from the calculations what the actual values are. So this here has gone down to 2,494. All right, we increase this further. Let's say I drop all the way to, I go all the way to 15. Okay, I go all the way to 15. Let's see what happens. These values change. Oh, I should have just circled it all up. This changes, that changes. All right, so this is 15. So we go to 15. Now you see 10 and 15. 10 and 15 is going to give us 25. 10 over 25 is equal to 0,4, right? 10 over 25 0,4. 0,4 squared in our formula times 25, no, times 15. Our resistance is 15, not the total, the load resistance. That will therefore be, probably I should have said here, IL by what? By L squared by RL. RL. maybe to, I almost made that mistake. Some people might make the mistake of putting the total there instead of here. We want the RR only. All right. So this will be this will then be what? 0.4 squared times 15 plus 2.4. It has gone down here to 2.4. Okay. Let's take another higher value. The trend, as you can see, is going down, but let's take it further. Let's say we take it to what? To 18. 18. What do you see? This here will be, if it's 18, that's 18. That's 28. These values change. This is times 18. But let me not squeeze it up. But this is no longer that. So this is now 10 and 18. 10 and 18 is 28. 10 divided by 28. Our current is 0.357. 0.357. Round it off, of course, to 3 decimal places. And then this here will be 0.357 squared times our load of 18. That will therefore be squared times 18. That gives us 2.296. 2.296. That is 2.3. So you can see as you go away further from the what? From the meshed impedance. We say impedance matching because when it was 10, it was meshed. Okay. Impedance matching is actually making sure that your load resistor, impedance matching is basically making your system impedance, what we would call R Thevenin or whatever, or R Norton. So I want to call it R Thevenin because I'm going to match with Norton as well. This is system impedance. That will be, must be the same as the load impedance. That way you've got maximum power transfer. You're going to have your maximum power. As you can see, our power peaked at exactly 2.5. Below it was slightly lower than 2.5. Rounding off, it makes it look like it was 2.5. Slightly above, it was 2.4 something, but running off is deceiving us. But you know it was exactly 2.5 there. And then you can see it drifted as we went way below. It was getting less and less, and as we go above, it's getting even less. Let's do two more. We do 19 and 20. This is double. It's not a fair comparison because here we had 1/10. The load was 1/10 of the what? Of the what call this, of the system impedance. But here it's only we're going to pick a double. Probably, let me just, for interest sake, let me just make it go up to, let me do my last one as 100, where the load is actually double. It's actually 10 times more. Right. I will make 20 just for the purpose of what we're doing, and then I'll just say if the load was a 10 there, let's make it 10 times more here and see. Okay, so this is 20 and 100. All right, maybe I should have ignored 19. There's going to be very little difference here, but anyway, we are here. This is 29. This is no longer true. 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 And that's 19. All right, so if we're at 19, this will be 10 and 19. That will be 29. 10 over 29 divided by 29. That will be 0.344. 0.345. If you round off, because it's 448, and then that will be 0.345, and then that will be what? Times 19, the load, and therefore this is squared times 19. That will be 2.25 2,259. 2,259. Okay, and then in that case there, that will be what? That will give us, oh, is that the power? 2,26 is dropped, it's dropping further. 2,26 is less than 2,3. Let's make it 20. So we are proving here that impedance matching, if you want to have maximum power transfer, you need to measure impedances. We are doing it through this exercise. All right, now this here is going to be 20. That makes 20 and 10, 30. That makes 1/3 is 0,3. Now this is 0,3 squared times 20. So that will be 2,2. That will be our power. As you can see, our power is 2,2. Back somewhere there. All right, well, this makes sense because this is actually half. We've moved half away from the load. Here we've gone double, so you can see it gives us the same value, 2,2. This was also 2,2. It was also 2,2, like that. So it shows that it's a perfect cone. It's coming down perfectly. All right, let's go to 100. I'm predicting now that 100 is going to give us 0,8. Let's see, the here it was 100, it was a tenth. 1 was a tenth. This is 10 times more. Let's see, if we have a load of 100, if we have a load of 100, this will be 110. 10 over 110, 1 divided by 11, is exactly what we had before, is it not? Why is it not like, I don't remember it being this, but anyway, just go on. All right, probably I might be wrong. Let's see. Squared times a load of 100, and that will be squared times 100. If you remember correctly, it is exactly what we had. It was 0,86. You can go back in the video and check. It was 0,86, which you rounded off to 0,8. So as you can see, the further you away you drift from the what? You drift from your meshed impedance, the lower your power, the higher the power loss is going to be. So it is best to always what? Maintain our power loss. Maybe I should have had 3 here. I should have written the currents in and the powers. But anyway, it was going to help us when we're doing what? When we're proving this with Norton. Now, as you can see, our peak power was when RL was equal to RS. Okay, this is where you get your what? Your impedance matching. So what do? You have to Thevenize or Nortonize your situation. Remember, that does not make any difference. Remember, getting the resistance, Norton resistance and Thevenin resistance, we are worried about impedance here. So it's done the same way. So you can Thevenize or Nortonize, and you still get what? You still get your what call this, your impedance is meshed, as long as you can what? You can make your load equal to your what? To your system impedance. Now let's just do one scenario with Norton and Norton thing. Just maybe 3 examples, just to show you that it will work the same. I will pick random examples. Let's say the current here is 10 amps, and the internal the system what we call the conductance. This is actually called the conductance. It's called 1 over Z, or this is the conductance, all right? It's not the impedance. It's an impedance when it's impeding. This way it's not impeding. Whatever is resisted here is forced to go into the system. So that is actually conductance. It's allowing this the load to have current. The higher the conductance, the higher what? The higher your what call this? Your the higher the current that is sent to the what? To the load. So look here, if we have a higher conductance, it means that this guy is going to send more to the what? To the load. This is our ZL. Alright. So now let's suppose that we have a current of 10 and an internal impedance of 1 and no. Yes, an internal impedance of 1. What I want to no, let's say 10, the same way as we did with the other one, and then let's make this one 1. I'm here. All right, if you do this, what is going to be the power? The power is going to be whatever current is here times that. All right, we're going to say, remember here we're going to use what voltage, what call this current divider. So we're going to say 10 amps is being sent here, and the current for the ZL is going to be determined by that conductance. So we're going to say 10 over 10 plus 1. Is this familiar? This is where we started. Okay, this is what? This is the I through the load. Okay, it's going to be that. Okay, that will be equal to exactly where we started, 10 divided by 11, and it's going to give us exactly where we started, 0.90. If you remember, this is exactly where we started. Now, if this is the current we have, it goes without saying that when you square this, when you square x squared this, remember again, power is still I squared R. So when you square this, it's still going to be 0.90. This is like deja vu. We're doing exactly what we did here. Let's see whether our answer is going to be the same. If it's not, it will be a miracle. All right, that will be times 1 because our load is 1. That will be x squared. All right, that will be this squared times 1. I don't have to say times 1. 0.826, exactly what we just got last, and this is what we said when we got the first time. So it's still, with Norton, it's still working out perfectly. All right, let's jump to 5 and see if we're going to get 2.2. Let's make this 5. Now this here is still going to be 10, but that there is going to be 10 plus 5. Okay, that will no longer be this. That will be no longer be that. It will be 10. It will be 2/3, right? This will be 0.6 divided by 15, which is 0.6666. All right, now if you square this, x squared times 5 and 2.2222, exactly what we got there. All right, this is exactly what we got there. This would have been 0.6 forever. Okay, this will be 0.6. We've done this, it's deja vu. We've done this times our load of 5. This is exactly what we have here, 2.22. All right, I'll go to the maximum power transfer to show that, to give us our 2.5 maximum power transfer. If the two are equal, this is where we're going to get our 2.5 amp current. Let's prove it. This is when the two are equal. Okay, so this is 10. Okay, this is 10. So it's 10 plus 10, 10 over 10 plus 10. That is 0.5. Oh, yeah, 0.5. And then 0.5 will give us 0.25. Square this. 0.25 times 10, which is 2.5. Right, and that's exactly our maximum power. Okay, we'll go and do this just to prove that it's basically it works the same way. We'll go and do the very last one, 100. The very last one, 100. This is 100. This is 10 over 110. If you remember, that's exactly where we started. 0.09, 0.09. Okay, let's prove it. If you have a calculator there, you prove it for yourself. 0.090909, and that squared times 100 is the previous calculation we did. Deja vu once again, and this is going to be 0.826, which is exactly that, but prove it to yourself. X squared times the load of 100 and 0.826. So you can see impedance matching is when your load is exactly equal to your what? To your system impedance. All right, thank you very much. I hope that made sense. I hope you can now answer questions on maximum power transfer. I have tried my best. Now it's your turn.